Hello, good morning, good afternoon, good evening, everybody, wherever we might be. It is my great pleasure and honor to welcome Henri, our old friend and my mentor for many, many years. And he's going to tell us about Prolate, Serendipity, and the zeros of Zeta functions. I try to understand this title, and I think in English it means luck, elongated luck with the zeros of Zeta.
You guessed right. Okay, now I will explain.
Yes, what. Yes, now I understand. At least I understand the title. Henri, the floor is yours. Take it away.
Okay. All right. So it started with a question or issue raised by Claude Shannon. I think even in his foundational paper, The Mathematical Theory of Communication, it was not phrased exactly like this, but it was implicitly there. So the question was, to what extent functions which are confined to a finite bandwidth are also concentrated in the time domain? A very natural question for the communication and the signal processing. So he was at the time at Bell Labs. And Bell Labs had a very powerful research group. So around 61, David Slepian and his collaborators, we'll see a little bit later, really solved the main problem, which was a sort of conjecture, but they called it the Folk's theorem, which was that the answer to this simultaneous concentration, bandwidth concentration, is like 2WT. W is the bandwidth and T is the time. And it was the answer for the dimension of the, or the dimension of the some space in which the concentration would be okay. The concentration refers to, you know, a function, which is a signal and its Fourier transform. I mean, function of time and its Fourier transform. So Slepian was very happy because they liked the problem, and they also solved it. And as he says, we solved it completely easily and quickly. Well, I don't know how easily, you will see. And the answer was interesting, even elegant and beautiful. That's where serendipity enters in this business, because as he says, the serendipity is that the solution seemed to hinge on a lucky accident, namely that we found a second order differential operator that commuted with an integral operator that was at the heart of the problem. So what was the integral operator? Well, this is another BC problem, not Baum-Cohn. It is a bandwidth concentration problem. To find the time interval of a given length for which the Fourier transform of the signal is maximally localized on a given frequency interval. That's W. I called it omega here for some reason. So what is involved? Well, in terms of the mathematical formulation, you take the projections onto the interval of time minus t to t, also the projection onto the interval of frequency minus omega omega. And then since you are dealing with the Fourier transform, you take the Fourier transform of the second projection. That's the Fourier transform which we are using. And then you form this operator which will measure the concentration in some way. And you see that it's a very friendly operator looking. It's a compact operator, even Hilbert-Schmidt, which you want to find the eigenvalues. Well, finding the eigenvalues is not an easy problem. I mean, looks like a very nice Toeplitz type operator, but still to find the eigenvalue was the main problem, in fact. So that's the serendipitous solution which arose when this group of people, Slepian and Pollack and then Landau, discovered that, in fact, this operator commutes with a second order, as in the previous slide, a second order differential operator. But let me stay on this slide and finish it. So what they found out is that they can compute the eigenvalues. They are all between 1 and 0, of course, for this compact operator, this kernel operator on L2 of the interval. Well, they wanted here to concentrate on the wavelength. And lambda 0 corresponds to the maximal concentration. But there are a number of lower eigenvalues which are very close to lambda 0. And in fact, they are all very close to 1, as we shall see a little bit later, which means that for a number of eigenvalues, you can get enough concentration to have a good signal. So later on, they proved indeed that the Folk theorem about 2WT was correct. Okay. So what was the lucky accident? I think I explained the serendipity so far. Yes, Piotr? The lucky accident was the existence of the second order operator, which commutes with both projections. Well, here from now on, I mean, since we are not really working on that BC conjecture, bandwidth concentration, I will take T and omega to be equal both with lambda. Lambda is the single parameter here. And so the operator which commutes with P lambda and P lambda hat, which in fact, it means that it commutes with the characteristic function of the interval minus lambda lambda and with the Fourier transform, is this W sub lambda operator, which you see over there, second order operator. Partial sub x means the derivative d by dx. It's a very nice operator. And that operator was known, in fact, for at least, I don't know, since 1880, when Niven wrote a book in which he also wrote this Prolate spheroidal coordinates. So this differential operator came from solving the Laplace equation in 3D. Helmholtz is called in physics. And it can be solved by separation of variables. You factor it, and you get, in fact, two ordinary differential equations and some other factor. If you do this, spheroidal coordinates. So the spheroidal coordinates are prolate because you look at the ellipsoid with elongated vertically, say, instead of horizontally. Horizontally, it would be oblate coordinates. Anyway, with this change of variables, one of the equations, ordinary differential equations you obtain, is exactly the one which is written here, expressing W sub lambda. And since they were interested, I mean, in physics or in solving the problem with boundary conditions on an ellipsoid, they were also interested in solutions restricted to the interval minus lambda, lambda. And on this interval, if you look at the equation, for lambda equals 0, you get the Legendre equation. And that equation is well known. It has the solutions are well known, the Legendre polynomials and so on. And this other operator is a bounded perturbation of the Legendre operator. So it's clear that it will have a good behavior, and indeed it has bounded eigenfunctions on that interval with eigenvalues which you see in the increasing order over there, and they form an orthogonal basis, a complete basis of the L2 space for that interval. So that was in fact well known before the 2WT problem, and they sort of, Slepian and his group rediscovered the fact that they can use this operator because it commutes with the projections and the Fourier transform to find solutions for the concentration equation. So they plugged in, because these two operators have common eigenfunctions. You take the eigenfunctions, which are called the Prolate spheroidal functions, and you plug them in, and you get the eigenvalues which they needed. So that's what's written here. PSWF means Prolate spheroidal wave functions. So they had the functions. There were books written about them at the time. They were quite well studied to some extent, not exactly what they needed, but then they studied them very carefully. So these are real valued functions. Psi n is even if n is even, and it is odd if n is odd. It has exactly n zeros in the interval, and it extends to an analytic function on the whole real line. In fact, in the complex plane, but they are interested in the real line. And they have a very good behavior. Even when lambda goes to infinity, they oscillate better than the Legendre functions, polynomials, or any other orthogonal polynomials, and give an optimal basis for the approximation problem they were interested in. So I'm writing here some of the properties of the eigenvalues now for the projections in which they were interested, for the compact operators they were interested in. And as you can see, they stay very close to 1 for some time. And then when they decay very fast to 0. All right, so that sort of ends the introduction into the story. There are lots of applications which were found of the work of these people: optics, laser modes. Slepian wrote about some of them. Signal detection, which is another theory than signal processing. Tomography, quantum mechanics, random matrices, as well as extensions of the method, namely the method consisting in this commutation. I mean, you have these compact operators coming from projections and their Fourier transforms, but you can take some other transforms, the Henkel transform or other transforms. They were applied to KdV by Grunbaum and his collaborators and two other integrable systems too. And I'll not get into that, of course, but it was very useful. Now, the next issue is, how did they enter in non-commutative geometry? Okay, this is what Alain did when he started working on the Riemann zeta function. So in the 1998 Selecta paper, the first long paper he published after his contrandu note, he showed that for global fields of positive characteristics, like function fields, he developed a trace formula which is equivalent, as I will say a little bit, with the Riemann hypothesis, not only for the Riemann zeta, but for L functions with the twistic Grossen characters. And okay, so that was, so he had a trace formula which formally gave exactly the right answer, but to prove that the convergence, of course, you need some cutoffs. So the cutoffs involve exactly this kind of projections onto intervals of finite length. And in positive characteristic, it works pretty well. And Alain showed that indeed, when lambda goes to infinity, the trace of the, so U of H, this is the unitary operator, this is the closed operator, which is generated by the scaling. And that's the operator whose trace he was trying to compute on the non-commutative space of the Adels divided, not by, of the Adel space which he constructed, a non-commutative one. And if you look at the statement, you see that the projection Q lambda is exactly on the space of functions such that f and the Fourier transform vanish for absolute of x, valuation of x large enough, which means that they are concentrated on an interval of length 2 lambda. So it's exactly the same type of concentration he was interested in, but then the limit gave the right answer for the trace, which is equivalent with the Riemann hypothesis, as I said. But now, in order to handle the Archimedean case, characteristic 0 is very different from a positive characteristic. So he needed an analog of the same kind of technology. And of course, that was involving the space P lambda followed by P lambda hat, the eigenspaces for the operator which I had on the previous slides. So this is how
if you don't mind me asking some completely simple questions. So what is this notation S of A, SCK? So these are, I understand, Schwarz functions, right?
Yeah.
Rapidly vanishing. But what is A, what is CK? I'm confused.
A is the algebra he was working with, but this is not relevant because
okay.
I'm not talking about the theorem which he proved in '98 on positive characteristic. Of course, you have to have an appropriate space of functions. This is S of A, and this is just to show where it enters. It's not that I would say much more about this.
Sorry, and this condition that the modulus of X is strictly larger than lambda makes sense in the positive characteristic, yes, but in the characteristic 0, it is vacuous, yes? It's
right. Sure, because there are no such functions. It's like, yeah, but that was exactly the problem they worked on, this Slavian people.
In positive characteristics, there are such functions, plenty.
Yeah, in positive characteristics, there are. That's a big difference, yeah, which arises, of course. Okay, and in fact, these Prolates spheroidal wave functions re-entered later. In fact, there was another, I'm only talking about selected papers. This is the second Selecta paper by Alain and by Katia Consani, which appeared last year, in which they prove wave positivity, a stronger version of the wave positivity in the Archimedean case for functions with a small support between 1 over square root of 2 and square root of 2. But that involves again the scaling operator. That's a generator of the scaling operator. And it involves the same, the compression now, not to the space, which was on the previous slides, where the functions and their Fourier transforms is 0, but on the space, of course, that one would not exist, but on the space in which the restriction to the interval minus lambda, lambda is 0 for the function and the Fourier transform. That's the orthogonal of the previous space, in fact. So the space of S lambda is the kernel of the sum of the two projections, the projection and its Fourier transform. They work here only with even functions, because this is what's relevant for what they are doing. And so now you know it's orthogonal. This is the orthogonal of the space from the previous slide, which was the sum of the image of the sum of the two projections. So that one is spanned by Prolates. I mean, Prolates plus minus their Fourier transforms. The even Prolates, because they work with even functions. And now they need is the orthogonal of that space. So since you have a basis of Prolates on one space, you can get some information about the orthogonal or the orthogonal of the orthogonal projection onto that space. So in other words, you can extract enough information for that, which they use to prove a trace formula. But the trace formula, as I said, unlike, it involved the scaling operator. But this time the scaling operator was compressed to this Sonin space. The Sonin space for any lambda is defined like you see here. They wanted it for lambda equal to 1. And, oh, sorry. And that kind of information, which they can extract from just being the orthogonal of the previous space, whose basis is known, allowed them to prove that strengthening of the trace formula, which implies wave positivity. And so in the Archimedean case. Okay, now, if you want to, advance on that direction, there is a hope that you can do better if you find the basis of the space, Sonin space itself. Because this way, since the scaling operator does not preserve this subspace, you can use W lambda maybe, the operator, which I talked about, this Prolate spheroidal operator, which you know that it preserves S lambda because it commutes with both projections and with the Fourier transform. So this leads to a search of extra Prolates, I call them here, because they come from trying to extrapolate the spectral investigation of W lambda from just the interval minus lambda lambda to the whole real line. But in fact, let me just say a little bit more about this W lambda. So W lambda was studied on the interval minus lambda lambda because that was the interesting interval for the problem they were working with, the original problem of the bandwidth concentration. But the Prolates, once you find the eigenfunctions, the Prolates, you see immediately that they, even from the fact that they satisfy the integral equation, you can see that they extend to the whole real line. So, and in fact, the operator exists on the whole real line. But Alain, from the beginning, in fact, when he saw that operator, let me just repeat some of the talk about some of the properties of this operator. I call them visible because some of them are obvious, some of them are a little bit less obvious, but they are visible. So that's the operator again, W, we are talking with. It's an unbounded operator with on the L2 of R. So Alain viewed it as an operator with core Schwartz functions. And it's closable, symmetric. It is invariant under the change of parity. And it is also invariant under Fourier transform. As you can see on the third line. Why is it invariant under the Fourier transform? Because formally, if you write it as a sum like that, what you see here is first the harmonic oscillator, which is invariant under Fourier transform, because that's what the Fourier transform does with the derivative and multiplication by x, and interchanges them. And then you see the scaling operator, the generator for the scaling operator, and it's adjoint. And if you put them together like this, you see that you get another invariant operator for the Fourier transform. So the big difference between the way in which the Prolate functions were used before and in which this technology was used by Alain is that it comes from the fact that if you look, in fact, at this operator, it contains the scaling operator in it. And then it makes, but the scaling operator, well, it's adjoint, does not commute with projections. But if you add this, I mean, the scaling operator cannot be compressed as is to the Sonin space. But if you add this harmonic oscillator, it becomes more manageable. The whole thing does compress. So I think Alain felt from the beginning that this operator should be taken on the whole line and not just on each portion of the line. Because, okay, so we have the operator it has.
Sorry, I'm having problems understanding this part.
Yes, okay.
So isn't the partial x just equal to 1? I'm sorry.
This is multiplication. I'm writing here operators. X means multiplication by x.
Okay.
So it's nabla x as an operator, partial x, then followed by multiplication by x. I didn't put any function here. I just wrote the operator.
Sure. But I'm confused. Yeah, of course. But I'm confused by this parenthesis here.
The parenthesis is that I wanted to isolate the scaling, which is the second parenthesis, okay?
Mm-hmm.
And the first
okay, I've got it. Yes, sorry, yes. Yeah.
The first parenthesis is the adjoint, just to show why they commute with the Fourier transform. The scaling itself doesn't, but if you put the Fourier transform in it, or after, it will commute with the Fourier transform.
Sorry,
Okay.
but the adjoint of the x is minus dx. So what is minus?
Doesn't matter. For the commutation of the Fourier transform. Oh, okay, sure. I mean, it's minus the adjoint. The argument was to make it obvious why it commutes with the Fourier transform, okay? Doesn't matter if it's plus or minus adjoint. Okay, so the other point I was trying to make is that for the Prolate people, the Prolates were, the main focus, because that's how you find the basis and the eigenvalues for the integral operators who are interested. And they were very happy that there is this W which commutes with it, and W being, like I write here, a Sturm-Liouville operator, a second order ordinary differential operator, which has two regular singular points, the finite ones, and two irregular singular points. It was, okay, it's a differential equation. You can write series solutions, and you can play with them and see when they are having good convergence, good properties, stuff like that. And this is what allowed people to find the Prolates and stuff like that. But I think from the point of view of what Alan was doing, the fact that it contains in it, in a way, the scaling operator makes it more relevant as an object of attention, the whole operator. Okay, so let me say that what he did was, as soon as he looked at what they do with the Prolates and the operator W, he looked at W as a whole on the whole real line. And as I wrote here with core the Schwartz functions, and he proved in his Collège de France course in 1998 that it has deficiency indices for 4. So the kernel of each side we should consider is 4. And also that it has a unique self-adjoint extension which commutes with 2 projections. Let me give a hint about how he proved.
Just a quick question.
Yeah.
The uniqueness is with respect to being a self-adjoint extension, yes? And this commutation
No, it has lots of self-adjoint extensions because the deficiency indices are 4 and 4.
But they are the same, yes?
Yes, so you can find a self-adjoint extension for any bijection between this kernel W, X, I, and the other one, plus and minus. I mean, von Neumann's theorem about.
Okay, I confused this theorem, sorry.
Yeah, it's okay. So no, it's the unique self-adjoint extension which commutes with 2 projections, or if you want, with P lambda and the Fourier transform. Okay, so, right, the computation of this deficiency indices, of course, I'm not going to give all the details, but it's coming from the fact that if you look at the equation which you want to solve, W psi is plus minus I times psi, or any complex lambda and complex conjugate. So each solution is analytic, first of all, outside the singular point. So on each subinterval is analytic, and it's uniquely determined by 6 parameters. Why? Because you have 3 intervals, from minus infinity to minus lambda, from minus lambda to lambda, from lambda to plus infinity. But since you have to have some matching at on the 2 sides of each of the finite endpoints, the singularities plus minus lambda, you have to have some matching, because otherwise the solution psi will not be in, and W psi will not be in L2. So it will not be, psi would not be in the maximal domain of W. So where do these logarithmic singularities come about? Well, because if you write the solutions around each singular point, minus lambda or plus lambda, one of them is bounded at the given point, lambda, the other one has a logarithmic singularity. So it's just elementary ODE to see that. And anyway, that's the idea of computing the indices. But then you still have to prove that it has a self-adjoint extension which commutes with multiplication by the characteristic function of the finite interval, and also with the Fourier transform. And he did that, and also he showed that that's unique. But so anyway, now we have a well-defined self-adjoint operator on the whole real line. And as I said, this equation, which I'm writing here in the form of a general Sturm-Liouville equation. This coefficient is called P of x, the first one, and then Q of x. So it's, as I said, of Sturm-Liouville type, and this is a class of equation which is very well studied, starting with Hermann Weyl. I mean, his thesis in 1909 was on proving criterion about the solutions of the 2 types of such equations. They can be limit circle or limit point class. There are 2 classes of such equations. And as I said, a very well-studied subject classically, by not only by Weyl, but then by Titchmarsh. Even Kodaira wrote a paper on that. And so, but the way they study it is on an interval. It can have singularity at the endpoints of the interval, but usually they focus on the interval. And there are, of course, extensions to 2 interval unions of intervals and stuff like that. But strangely enough, I mean, and there are several good books about Sturm-Liouville, more than 3 or 4, very good, but with lots of examples. It's strange that they didn't look at this example. Probably it's because from their point of view, it doesn't behave so strangely. Since if you look at the equation on each of the 3 intervals in which the singularities split the real line, if you just look on an interval, the type, the class is limit circle only. Limit circle is much, for them, it's much easier than the limit point. Why? Because limit circle at both endpoints makes the spectrum to be discrete. Most of the literature is looking at the case when the spectrum is not discrete and trying to find the spectral measure. And that's where the sort of bulk of the work in the Sturm-Liouville theory is, finding the good formulas for the spectral measure. Well,
Ari, sorry, so this LC stands for the limit circle, right?
LC is a limit circle, but I added some other things which I will explain.
Okay.
So it is a limit circle, but limit circle comes with two sub cases. One is if the solution has finitely many zeros in an interval from the singularity 1, or it has infinitely many zeros. If it has finitely many zeros, it's much easier to study. It's called non-oscillatory. If it has infinitely many zeros in each interval around the singularity, then it's oscillatory and it's a little bit more difficult. So about this equation, on the finite interval minus lambda lambda, that's the easiest because it's LCNO on both ends, which means that it's non-oscillatory. And you can see that it's non-oscillatory because when I talked about the solutions are for the finite interval are in fact the Prolate spheroidal functions. And as I said, the Prolate of order n, psi n, has exactly n zeros. So you know exactly what happens. Whereas if you go from lambda to infinity or from minus infinity to minus lambda, the solution, the Prolates, by the way, remain solutions on the whole real line. On the other interval, they are still solutions, but they have infinitely many zeros. They oscillate. As I mentioned, they oscillate more uniformly than other orthogonal polynomials as lambda grows, but there is still oscillation. Okay, so now, so my guess is that they didn't look at the spectrum for the other the infinite intervals because from the point of view of the spectral measure, it was not that interesting since it is discrete. It's discrete on both infinite intervals too. Because if you have, if you are in the LC case, no matter if it's LCO or LNCO, it was known that the spectrum was discrete. Okay, so let's look again at how to study the spectrum. Well, for this, it's not enough to know that you have this self-adjoint extension. You have to identify the boundary conditions which define the self-adjoint extensions, because the main thing in the Sturm-Liouville theory is the classification of the self-adjoint extensions of these Sturm-Liouville equations. And that classification is in terms of boundary conditions, like is exactly what they do in differential equations. Okay, so in the case we are looking at, now remember that Alain was looking at the full real line. And this is when, in fact, we started working on this problem and focusing on it more seriously, namely to find exactly as much of the spectral properties as one can for this operator on the whole real line. So the boundary conditions which define the self-adjoint extension, which Alain found in 98, is that at the finite points, you have to have this limit equal to 0, which means that, for instance, plus lambda, it just means that lambda plus x times the derivative, they tend to 0. Well, it turns out that this condition is the same, is equivalent with another boundary condition, namely just saying that psi, the solution, is regular at the as it approaches the point lambda. So it's bounded. It's bounded on the interval near lambda or minus lambda, depending on you are with the boundary condition. So the first boundary condition, the one which I wrote here, was known. And in fact, the fact that there is that the self-adjoint operator, if you look just at the interval minus lambda lambda with this boundary condition, it was known that this is the only self-adjoint extension. It's a paper by Katz-Nelson in which he does this very carefully. And he looks at all other self-adjoint extensions and gives a nice classification of the boundary conditions. Anyway, that part was known, the restriction to this interval. But when you view the operator as a whole, of course, there are boundary conditions also at plus minus infinity, which are the irregular singular points. And I'm writing them here, splitting it into even conditions for even functions, which I put a superscript plus, and conditions for odd functions. So for even functions, you see here the condition, and this is for odd functions. But actually, they can be rephrased to a little bit easier, and I'll show you later. But let me just finish with this slide. So the theorem which we proved was that the spectrum of the self-adjoint extension found by Alain is discrete and unbounded on both sides. The negative eigenvalues are simple. The positive eigenvalues are double. And why are they double? Because you have positive eigenvalues coming from the prolate functions, which were eigenfunctions for the finite interval, but they extend to the full real line. And of course, they remain solutions and they have the same eigenvalues. But on the other hand, if you just look at the operator restricted from lambda to infinity, say, that's an operator, again, of Sturm-Liouville type with LC conditions on both sides. But one of them is oscillatory at infinity. And then it's known that such operators will have infinitely many, of course, a sequence of eigenvalues, which is unbounded on both sides. So you will gain some new positive eigenvalues and some negative eigenvalues. Okay, now with possibly finitely many exceptions, well, this refers to the fact that we don't believe there are any exceptions, but there could be some new eigenvalues which are still positives, and they are not prolates. Unlikely, but I'll clarify later why only finitely many exceptions are possible. Okay, so let me just give some hints about the proof. As I said, the compression to the finite interval, that was a known operator. It's a positive operator. It has simple spectrum, and that's the one which is known. Now, if you restrict it to the the rest of the real line, of course, it has two sides. The one is up to from lambda to infinity. The other one is from minus infinity to minus lambda. So it's enough to look at one of them, which I call W prime SA. So it's a compression of the operator with orthogonal to P lambda. Oh, by the way, this is the first typo I see. That's a capital lambda, not a small lambda. It should be the same lambda here. Okay, and now if you use the decomposition into even and odd functions, because the Fourier transform preserves both of them, this you get a further splitting of this into the even part of the operator and the odd part of the operator. And as I said, each of them comes under the classical standard Sturm-Liouville theory, and you know that it has a sequence of eigenvalues which is unbounded on both sides. Okay, that's what I'm saying here. The spectrum is discrete, simple, unbounded on each side. It's unbounded because it's LCO on both sides, this oscillatory behavior. So this W prime inherits, for some reason I dropped SA here, inherits the positive eigenvalues corresponding to the Fourier transform of the Prolates. Okay. So that's why you get multiplicity 2 for the full operator. Now the spectra of the two parts, even and odd, are disjoint because the boundary conditions at infinity exclude each other. Let me remind you that for the even functions, you have this boundary condition with x sine or something. The other one is cosine. So you cannot have both satisfied. We are only looking for both even functions and odd functions. It's enough to restrict to the interval from lambda to infinity because you know that they are even or odd. So the other part from minus infinity to minus lambda is behaving in the same way up to the sign. Okay, so that's the information about the spectrum. Now, what can we do about, well, finding extra prolates? So you have information about the spectrum, but you still have to find eigenfunctions. Now, as I said, being an equation which was as a differential equation, it's well studied. There are several papers by Ramis and collaborators in which they find the asymptotic expansions of the solutions around each singularity. And using this, we prove the following lemma that if you look at the equation W psi is equal mu times psi, so mu is a tentative eigenvalue, but you don't know that it is, the asymptotic expansion of the unique solution, which behaves at infinity asymptotically like this. So you see, that's how you can write the boundary condition, by the way. I mean, the boundary condition which I wrote as a limit on that slide, so an expression with two terms, in fact, it's equivalent to saying that asymptotically at infinity, the even functions should behave like sine x over x, and the odd functions like cosine x over x. Okay, so that solution is Borel summable and equal to the Fourier transform of the unique solution, which is even, which is 0 on the interval minus lambda lambda, but agrees with F mu on the part which is bigger than lambda. So as I said, from Ramis and Altera, you can see the expansion of this solution F mu, which is finite at lambda. But we take now the solution phi mu, which is 0 on the interval minus lambda lambda, but agrees with the expansion in the rest. Okay. And as a corollary of this lemma, okay, you see that if mu is an eigenvalue, a negative eigenvalue, then this solution given by the lemma, it was Borel summable in general, but it will be a solution if mu is an eigenvalue, then this function belongs to the Sonin space. Why? Because now mu is a negative eigenvalue. So it's orthogonal to the space of positive eigenvalues. And so it belongs to the Sonin space because the Sonin space is the orthogonal of the space generated by the prolates. Okay, so this is how one can begin to find these extra prolates. I mean, the eigenfunctions for negative eigenvalues. All right. So why is this good? Well, if you look at the semi-classical approximation of this situation, just to see what will happen. So the Hamiltonian, which one can write, will have this form. But now, unfortunately, the notation clashes here. P and Q here is position momentum. That's a standard notation for Hamiltonians, which we cannot change. So it's not the P and Q from the Sturm-Liouville. Now, the correspondence Q goes to multiplication by X and P by the derivative. And because of the Fourier transform we use divided by 1 over 2 pi, gives the W lambda is a semi-classical version. The Hamiltonian would be related to the Hamiltonian by this relation. So the H lambda is the one you see here. W lambda and H lambda are related by this. There is this factor of -4, which will reappear in a lot of the formulas which follow in a way, hidden in a way. Okay. So I have to signal it. So now, if you look at the number of counting functions for negative eigenvalues of our operator WSA, eigenvalues which are negative, but which are less in absolute values than E squared, not E, but E squared, then it's equal to 4 times, this 4 corresponds to the 4 here, where the number sub S means that it's the semi-classical approximation. So the semi-classical approximation for the counting function of eigenvalues is very close to the Riemann's asymptotic formula for the zeros of the zeta function. That's the first signal that this operator has something to do with the Riemann zeta function, and its negative eigenvalues, which are significant for this relationship. So the idea of proof is here. The Sonin space, of course, corresponds to the big I made the same typo here, Paul. It's big lambda, not little lambda. So the Sonin space corresponds to P squared greater than lambda squared, Q squared greater than lambda squared. The region for the counting of the eigenvalues is the one which I write here. And its area can be computed. it involves using some elliptic integrals, but it can be computed. And this is why you get this estimate. So the semi-classical approximation tells that indeed, I mean, this extension of the operator and its negative eigenvalues have something to do with the zeta function in a way which is still mysterious. Okay, so let's go to the, but we saw that we had to take some squares. So let me go back. You see here, in this approximation, we took the squares of the energy where you stop, which means that to get to the zeros of the zeta, you have to take a square root. So now the negative eigenvalues, as we saw, come only from the restriction to the big interval, lambda, that's always capital lambda, lambda infinity. And so you look at this restriction, the same note, now I come back to the notation P of X and Q of X like in the Sturm-Liouville, not the semi-classical, not the phase space notation. And what we want is to get a factorization, which will be like taking the square root of the operator W. Now, you see, this W operator, in a way, it reminds of it should be like the analog of something, a Laplacian, but not a Laplacian for a positive metric. It should be like a Klein-Gordon type of Laplacian with a metric with a plus-minus signature, not just plus, not positive definite. To extract them, so what we want to do is to construct some Dirac type operator. This will be, in fact, closer to the way in which Dirac did that, because he did it for the Klein-Gordon equation, or independently, probably. But he was taking a square root of something which is not positive definite for a metric which is pseudo-Riemannian, not Riemannian, Lorentz type. Okay, so for this operator, you will need a connection. So the connection comes from solving a Riccati equation, because you write what you want to get. You want to get a connection for the operator so that if you take its square, you get W. Well, if you write what you need, then it comes as you get this Riccati equation. And this gives you a factorization. This is a type of factorization which is called Darboux factorization in this area of factorizing operators, differential operators. So W restricted to this interval factorizes as a nabla plus and minus a solution of the Riccati equation. Nabla is the derivative by X, but it's backed up on both sides by this factor of P, which comes here. That's a type of factor which comes in when you do a Liouville transform of the equation, second order equation, to bring it to the standard form, like only the second derivative plus potential. So all the solutions of this Riccati equation are of this form, this nabla U divided by U. But to divide by U, you need the solutions to be non-zero, or to have no zero on the real line. And because of the oscillatory behavior, as I mentioned before, at infinity, the solutions of the equation W applied to U is equal to 0 on this interval, they will have always infinitely many zeros. All solutions, real solutions will have zeros. So you have to take a combination of two linearly independent solutions with a parameter z, which is not real, because on the real line, they have plenty of zeros. And this introduces the complex numbers in this business in a way. I mean, you cannot work with real solutions and find good connections, which in a way gives an indication that this Dirac will not be like the Dirac for the circle. I mean, it will be more like the Dirac on a Riemann surface. It will have, but the Riemann surface this time will have not a positive definite metric, but one plus minus. So it's a little bit of a strange thing, but okay. So then the next proposition is that if you have a solution of the Riccati equation, you form the operator, which we use the same symbol as for Dirac, which you see here. And it has a domain which comes from its expression, psi and psi tilde, where the psi tilde has to satisfy this condition, that its derivative with respect to this connection fits in the domain of the ordinary W prime restricted to even functions. Okay, the square of this Dirac is a diagonal operator. These two operators are isospectral. The second one is our operator we wanted to extract square root. The other one is isospectral to it, but it's not a self-adjoint operator because you have this complex function in it, complex valued function. It's Dieudonné called them quasi-Hermitian, these operators which can be made self-adjoint if you change by a change of metric in the Hilbert space. And that's exactly what happens here. So the square of the Dirac is not exactly a self-adjoint operator, but almost. I mean, it's the lower one is only quasi-Hermitian. Anyway, the spectrum of this Dirac, of course, is made of the square roots of the eigenvalues of W prime. And W prime, remember, it has positive eigenvalues and negative eigenvalues. So the spectrum will have, if you take the square root, will have imaginary numbers, not just positive numbers. Okay, now, I mentioned before the Riemann's asymptotic formula for the number of zeros less than a given imaginary part less than a number e, positive number e. It's roughly this. Well, we computed the similar number or the counting function for the operator, which we now have. So now we have this Dirac operator. You have to multiply it by 2. This multiplication by 2 is still an echo of the fact that there was a factor of 4 in front of between the Hamiltonian and the W, and also a negative sign. For the Hamiltonian, for instance, the negative eigenvalues here become positive because there was a negative sign. So the spectrum of 2D is discrete, simple, contained in what I'm writing here. Its imaginary eigenvalues are symmetric under complex conjugation, and the counting function behaves almost exactly like this formula, very close to the Riemann's estimate. What does it mean? Well, it means that the ultraviolet behavior of the spectrum for the negative eigenvalues of this operator is very close to how the zeros of the zeta behave, the non-trivial zeros.
And this counting functions, it counts what? One more time with NDE?
It counts the number of eigenvalues which in absolute value are less than E.
Okay, good.
E is a positive number.
Yeah.
Okay.
Thank you.
So just a hint of the proof. So if you make a Liouville transformation, I think I mentioned briefly before, you bring it to the standard form, this Sturm-Liouville equation, which is a second derivative and then some potential. This is a potential. There is a formula proved by a guy, Haywood, I think in the 40s or 50s, probably. Yeah, in the 50s. He was a student of Tishmash. For the counting function, for these Sturm-Liouville operators of this type, of the type which I'm writing here, with conditions on the potential, of course. And his formula would not apply directly to our potential, but there were improvements of his formula. In fact, he has a formula for the positive eigenvalues and one for the negative eigenvalues. So his formula for positive eigenvalues is ours for negative eigenvalues because of the change of sign. And that's Haywood's formula. And now you have to compute this. You have this potential Q, and the computation involves more of the elliptic integrals which you saw for the computation of the counting formula in the Hamiltonian case. This is a more delicate computation, but it can be done. And that's the computation which gives this counting formula. And as you can see, this formula is an improvement over the counting formula for the Hamiltonian, because that one didn't have the log term which appears in the Riemann zeta function counting formula. And here is a plotting did by Allen's big computer of the imaginary parts of the n. So on the horizontal, you see n eigenvalues for the operator W SA and the imaginary parts of the zeros of zeta, and the zeros of zeta are in red, the other ones are in blue. But if you see only red in many places, is because when red covers blue, you only see red. So it's almost so close that they cannot be distinguished in the picture. Anyway, it's pretty close, very close. So numerically speaking, this is okay. How about the positive eigenvalues? Well, the positive eigenvalues should be related to the trivial zeros if there is some justice in this world. So indeed, if you look at the positive eigenvalues, we know that they come from the prolates. In the even case, chi2n. And as I mentioned, there is a Haywood's formula also for counting the number of eigenvalues, which for Haywood were negative, for us will be positive, less than a given number. That formula, I didn't write it here because it's a little bit more complicated than the other one. But anyway, if you look at that, if you use his formula, like we used the previous one, you see that the counting function, again, differs only by a bounded amount from the counting function for the chi2n's, which implies that there are at most finitely many positive eigenvalues of this W prime self-adjoint, this part on the even functions. there could be only finitely many which are not coming, eigenfunctions which are not prolates. So this, in fact, should be shown that there are no other positive eigenvalues than the one coming from the prolates. But if there are, that could be only finitely many. Okay, now if you look at the asymptotic formula for the eigenvalues, as I said, the prolates are very well studied. So they have asymptotic formulas for what happens when n goes to infinity. So independently of lambda, when n goes to infinity, they behave like this. You see, up to a bounded term, they are of this form, which means that if you take the shift minus square root and minus 1/2, you get exactly 2n, which are the zeros, the trivial zeros of the Riemann zeta. So in fact, the positive eigenvalues of our operator, the big operator, match the squares of the trivial zeros of the zeta. And so the matching in this rough matching, which is in ultraviolet spectrum, I mean for large end, and it's, you can see it from these counting functions, mimics pretty well what happens with the zeros of the Riemann zeta function. Okay, what could be the geometric meaning? Well, this is very speculative. But as I said, if you, by analogy with the Klein-Gordon equation and with the Dirac equation, first of all, although this W is an operator on the real line, because it has this mixed spectrum with positive and negative, it would be like sort of analogous to a Laplacian corresponding to a metric which is not positive definite, Minkowski type or Lip or pseudo-Riemannian, not Riemannian. So there is no such Riemann surface of signature +1, -1, but there are two-dimensional manifolds which are studied by physicists as first as a toy model, but they proved useful in the modeling of the black holes. So, but first, before getting to that, let me finish what's on this part of the slide. So this Dirac operator is not self-adjoint, is not skew-adjoint. So what kind of a spectral triple can be made out of it? Well, it has some good feature because the resolvent is compact, and there is an algebra of functions which has bounded commutator with D, because these are functions Lipschitz for the metric dx over x, not dx, but this operator is related to the scaling operator, as I said. So if you see it like on the positive part of the real line, that's the metric dx over x. Anyway, to account for the real and the imaginary eigenvalues of the square, you should look for a two-dimensional metric with signature -1. There is a class of metrics in two-dimensional black holes, which are, as I said, studied by physicists, and the class of metrics, which fits with what we have, is of this form. You have a function here multiplying dt squared, and you divide by it and change the sign. And this corresponds to a two-dimensional black hole in three-dimensional space-time with horizon where this vanishes, event horizon, which satisfies the analog of Einstein equation. And if you compute the cosmological constant which enters into that, is 8. because it comes from differentiating this 4x squared twice. And it has no source because the source would introduce another term. So there is an analogy with a sort of matrix on some sort of Riemann surfaces which don't exist, like black holes. Okay, so let me summarize now. I said, so first of all, W I think it was written on the slide, but I didn't mention it. The counting function was done for lambda equal to square root of 2. The calculation of the counting function, because that's a precise calculation. If you change lambda, the elliptic integrals change. It would be very difficult to have a formula for a general lambda, but in principle, yes. So, but anyway, for square root of 2, because the two examples which are interesting, because there are things to compare with in the literature for the Riemann zeta function, are lambda equals 1 and lambda equals square root of 2. So for square root of 2, this gives an example of a self-adjoint operator whose spectrum matches to a remarkable degree that of the zeros of the zeta function, both the trivial zero and the non-trivial zeros, of course. The eigenvalue counting formula for this operator is better than the semi-classical one, which, you know, the semi-classical one, you can write a Hamiltonian without having any specific operator in mind, just a class of operators. Well, for this one, you get a better estimate, which means that it's a very good candidate to look at. So the Dirac operators, as I said, each Dirac operator is given by a connection. That connection cannot really be optimized in any obvious way. So it's just a solution of the Riccati equation. So any Dirac, you can take any Dirac, and it will have the same spectrum. And that spectrum at the ultraviolet range behaves as the zeros of the zeta. And let me remind you what I said at the beginning, that for lambda equal 1, W1, which preserves the Sonian space now, that's exactly the Sonian space which occurs in the Con-Consani proof of the wave positivity at the Archimedean place for functions which support here. So it fits with that. And finally, if you click on this, you can get to more details because the paper is now online, but it's not yet open access. So if I click, let me see what happens. Oh, yeah, you say get full access
to this article, yeah,
through the library, maybe.
Mm-hmm.
Okay. All right. So let me see, where is my Zoom? Now I lost.
We see your screen, but not your slides.
Yeah, but why?
Because you clicked on this link and you were redirected to.
Okay. So let me come back. History. Let me see if I came back.
I think, Henry, you need to click the PDF reader like this.
Yeah.
No, I have to link again. Wait, what is this? You are screen sharing.
Well, we are sharing your screen, which is good. Don't you have your slides?
Oh, I have my slides.
I see them here in the corner. Prolates PDF, isn't it this one?
Yeah.
Around here?
Okay.
Yeah.
Do you see that now?
Yeah, but you should make it full screen.
Yeah.
Yes, perfect.
Okay. All right. So I'm ready for questions now.
Okay, so thank you very much. And now we enjoy the question time. So maybe first any comments from the co-author? Alain.
Yes, well, I have just one comment, which is that there was a typo in the page just before the end one, because it's not a 3D, it's not a 2D black hole in 3D, it is a 2D black hole in 2D. Because in the two-dimensional.
Yeah, I don't know why I put this.
It was at the end. Yeah, you say this geometry
Yes.
corresponds to a 2D
yes.
in 3D space-time.
It's in
Now,
2D, yes.
In 2D. But what happens is that one can embed this 2D
Right.
Minkowski geometry in 3D flat Minkowski space. And it gives a very beautiful picture, actually.
Oh,
So,
maybe
but it's really 2D. It's really a 2D, two-dimensional black hole.
Can I? It's Ludwig. Hi, Henri. Can I continue? But the whole operator, the Dirac operator, is one-dimensional. Do I understand correctly? So this two dimensions is just analogy.
Yeah, it's one-dimensional, but it's with a bundle which is two-dimensional, with coefficients in a bundle, right? I mean, if you take the operator over Dirac over one-dimensional manifold, what do you get? You get d by dx, 1 over I, d by dx.
Yeah, but the metric is not positive definite, so there are some complications.
Yeah. Yes.
But anyway, so if it is one, so the connection preserves this metric. Is it a metric preserving connection? This which you add to the?
Well, you cannot. We cannot say that because, I mean, the connection. It would not be a Levi-Civita connection. No, I don't think so.
Okay.
May I ask a bold question?
Yeah, go ahead.
Okay, so what do you expect this to give with regard to the Riemann hypothesis?
Well, what we expect is that it will fit with one of the trace formulas which Alain was developing, namely the one which uses the compression to the Sonian space. But it has to be corrected, of course, with the contribution of the primes. I mean, one could never expect to get just from the Archimedean place solution to the Riemann hypothesis. You need to correct it with the primes. And then this will have to be extended to the other local fields, local places. This is just one local place, which gives the sort of the main kind of behavior, but then it has to be corrected, of course.
Can I add something, Riku?
Yeah, of course, please.
Yeah, so I mean, I think what you see there in this operator corresponds to what Riemann did as a computation when he wanted to have an idea of the behavior of the zeros.
Yeah.
And so this operator is taking into account correctly the Archimedean place. Now, what happens is that we also know for a completely different reason in the work with Consani how to understand the low-lying zeros of zeta by using a few primes. For instance, by using the integers 2, 3, 4, you can understand the 31 first zeros, again using the Prolate functions. So the big question, which is totally unanswered, is to combine the two. And the very tempting way of combining the two is to replace the treatment here, which is on the real line, by the treatment of the product of the real line by finitely many p-adic fields, where there you have to divide then by a discrete group, which is the group of powers of these primes. Once you do that, what we expect in the work with Riku is that there will be an analog of the Prolate operator and an analog of all this analysis, which then, when you will compute the corresponding spectrum, will begin to combine together the two situations. Namely, it will keep the same ultraviolet behavior, but it will give an extremely good approximation to the first zeros, depending on the number of primes that you have been using. So this is a strategy that we plan to apply, working with Riku and Katya at the same time. Because I mean, the work with Riku is really ultraviolet. It was totally unexpected. And the work with Katya is really the infrared. Namely the fact that, for instance, we could find an operator theoretic incarnation of the Riemann-Siegel formula. The trouble was the following, is that this operator theoretic incarnation was at the ultraviolet level, like the Dirac operator on a circle. So of course, it's not good at all. So one has to combine the two in a subtle way. And of course, we are very, very far from that.
Yeah. What I can say is that, yes, it was just on the circle, but it's also part, as I not said from one of the first slides, it's part of this W operator, the scaling itself.
Yes.
Which means that if you correct it, it becomes, closer to the Dirac which we got, and then it should have a better chance of working right.
Tomek? Go ahead, Tomek, show yourself.
Yes, I'm trying to show myself. I have a question. So this ultraviolet part of the spectrum corresponds to, in a sense, to a distribution of primes. I'm not sure if I understood Alain's comment about this infrared part. Does it have some arithmetic interpretation? Or is it something completely different from arithmetic?
Should I answer, Riku?
Yeah.
Yeah. Okay. No, I mean, you have to be very careful because you see, the fact that, I mean, there is a duality. It's not the same thing. The zeros of zeta are not, they are just dual to the primes, okay? They are dual to the primes, but what you find out when you study them, and this was found by Riemann, is that you can just not, it's not enough to put the primes, you have to put the Archimedean place. And somehow, if you want, the main behavior of the zeros comes from the Archimedean place. Doesn't come from the primes. The primes do very tiny corrections to what you get from the Archimedean place. In fact, this can be seen in Riemann's paper because he only uses, if you want, the Archimedean place to make his computation of the number of zeros. Now, and this is also very well known in the understanding by people in random matrices of the way the zeros of zeta behave, because they behave in a certain way, and then you have this additional contribution from the primes, which is sort of, additional. So what happens is that for the infrared, what was really the key was inputting a few primes. As I said, with a few integers, with the integers 2, 3, and 4, you already get an extremely good approximation to the 31 first zeros of zeta by an operator. This operator is obtained from a Dirac operator on a circle, which is rather stupid, but conditioned by Prolate functions. Now, because this operator has a bad behavior at ultraviolet, you cannot hope anything. So if you want, what one needs to do is to, instead of conditioning the Dirac operator on the circle, using these Prolate functions for finitely many primes, I mean, the integers enter there, one will have to do something similar conditioning for the operators that we found with Riku, namely the one which has the correct ultraviolet behavior. Okay. And in order to do that, because you have to input finitely many integers or finitely many primes, you no longer have to work directly in L2 of R even functions. You have to input the periodic numbers. So that's what happens. But the beauty, if you want, one thing which is extraordinarily important is what Weil had found. Namely, Weil had found an equivalent to the Riemann hypothesis, which is some positivity. That's what we proved with Katya for the case of the Archimedean place. But the point of this equivalence is that it only involves finitely many primes at a time. So it's enough to understand the situation with finitely many primes in order to prove the full thing. You don't have to look at infinity and so on. I mean, this is not the point. The equivalent, if you want, the operator theoretic incarnation has to be found only for finitely many primes. You don't have to input all the primes together. This would be a big mistake, because then the analysis would be impossible and you would run into a loophole. I mean, you know, a vicious circle.
Mm-hmm.
Okay, thank you very much.
Well, one last remark would be that it's what's interesting is that this operator we were studying, I mean, it was so well studied on the finite interval, and it was used only through its input for that finite interval. It was also used in connection with the Riemann zeta function, because Montgomery and then Odlyzko were looking at random matrices and, you know, the Gaussian unitary ensemble and stuff like that, and showing that it fits with the distribution of the zeros of zeta. That kind of work involves the integral operator, which was on the first slides, P lambda hat P lambda. It involves its kernel, the sine x minus y over x minus y. That's the one which enters in a determinant or something through which they can evaluate the measure for those Gaussian ensembles and stuff like that. But the negative spectrum of the full operator is sort of was ignored in a way. This is very strange, and it indicates that this operator has some mysterious connection with zeta, which you cannot see, but just the fact that it contains the scaling operator, which was used by Alain in all the trace formulas, the semi-classical one and the one at the beginning, and the other one, which involves the Sonin space, it shows that it brings in some new essential contribution in this direction.
Yang, go ahead.
Hi, Henry. So yes, my question is, so you showed that there is a graph, right? So like to show this overlap, these blue dots and red dots.
Yeah.
It means that we do have some like a numerical methods to somehow reach the eigenvalues, the spectrums of
course, but this is how the graph was done. You have numerical methods, but numerical methods will never prove the theorem, because the zeros are also obtained by numerical methods, not exactly. Mm-hmm. And the eigenvalues are they are also obtained by numerical methods. So numerical methods give you an indication of something, but it cannot replace the exact theory.
So, okay, so then do we have in this method, do we have some sort of asymptotic understanding of these errors, like through this?
Yeah, that's exactly what we have, an asymptotic understanding. But I mean, there are, this is far from being enough to settle the problem.
Okay, so this method is known from the literature, or like it's a new part of the new results in this work.
What is new for the zeros of zeta? Yes, I mean, there are lots of numerical studies. For the eigenvalues which we found, no, it's only the ones. These eigenvalues are new, completely new. I mean, nobody was looking at them, or at least nobody traceable.
So the method you probably refer as like semi-classical analysis or something. That's somehow the
no, the semi-classical approximation is something which is routinely done when you have, you know, Schrödinger type equation. That's how you approximate things first.
Adam?
Yes, you said that this counting function for W lambda for lambda different than square root of 2 is somehow more difficult to compute, yes?
Alan is
Yeah, no, I mean, it's not that it's more difficult to compute. You have a formula which depends on lambda. There is a kind of Wien displacement law, which tells you exactly how it moves when you change lambda. But the correct values of lambda to get, if you want the same formula as Riemann, are lambda equals 1 and lambda equals square root of 2. And lambda equals square root of 2 is the best, because it relates also to the type of things, you know, that you expect for the Archimedean place. But let me just add one comment, you know, which is that in some sense, there is another serendipity which took place here. Is that when Henri and I started working on this problem about a year ago, I mean, a year and 3 months ago, we had absolutely no idea that there would be any relation with Zeta. We had absolutely no idea. I mean, we were looking just for the fun at this operator on the full line, which I had not done in the 98s, you know. And so, I mean, first of all, the first surprise was that the operator had discrete spectrum, because, okay, I mean, one could expect that it would have continuous spectrum, then you can get nothing.
Yeah, like the genre, yes.
And then, you know, the fact that the zeros were beginning to look like the squares of the zeros of zeta, that was a total surprise. I mean, if we had to write a proposal for, and so on, we could never guess what we are going to find. Never, never, never.
Yeah, this is a typical project NSF would not fund. I mean, we didn't know, we didn't know even that the spectrum is discrete. I mean, the Legendre equation has a continuous spectrum on the infinite interval. Of course, it's not a bounded perturbation of the Legendre if you look on the real line, but it's a pretty mild perturbation. So you can think that it will still be maybe continuous with some interesting measure, but not related to the Riemann zeta anyway. I mean, we didn't have any idea about it. It was just pure curiosity.
Can I ask about Henri and Alain? So the right, let's say, class of Dirac operators would be not.
Sorry, Ludwig, why do you keep your finger on the camera?
So if the right class of Dirac operators should be with compact resolvent. That's what you, not necessarily self-adjoint. That's what you more or less suggest.
Yeah. But with a square self-adjoint. You see, I mean, we have to push the framework of commutative geometry a little further, because first of all, okay, we have to handle Minkowski, and second of all, I mean, here it's clear that it is a square of the Dirac which is self-adjoint. It's not the Dirac. The Dirac is never self-adjoint because it has imaginary and real eigenvalues. So.
And even this is not completely self-adjoint.
Yeah, you're right. We have to alter a little bit.
Okay.
up to a change of,
Yeah,
well,
sure.
which means that the two spin bundles, spin plus and spin minus, have each
Yeah,
own,
sure. That's perfectly fine.
right, their own matrix, yes. But then it can be made self-adjoint indeed. I mean, change of it.
Good, thanks.
Jonathan, please.
Yeah, so one thing that was very intriguing was this thing at the next to last slide. If you just back up one there.
Number 19.
I think it was 19. The connection with the black hole. So is there any kind of even like heuristic reason to expect black hole physics to have anything to do with zeta functions? I mean, if there were, that would be a very kind of intriguing idea that might play off, have other ramifications, not necessarily for this, but for something else.
Well, it's hard to say. It's just the fact that they do use, you know, indefinite metrics, which makes us connect with them. But otherwise, I don't know. Maybe Alan knows more.
Yeah, well, there is something to be said in that respect, yes, which is that when you look at this corresponding metric, you find that in the time variable, you can make it periodic. So in other words, you shouldn't think of it as being, you know, kind of huge in the time direction, in the t direction, but you should compactify the t direction and make it periodic. And when you do that, I mean, then in the limit, when you make the period very small, you do obtain exactly the type of Dirac operator we had. So the link is rather strong in that sense. And then, I mean, there are several things which have to be, I mean, for instance, okay, there is a cosmological constant in the corresponding black hole. So, but obviously, if you want the what is behind is a little bit like the realization of what Zellberg was trying to do. Zellberg was trying to obtain a link with the Riemann zeta function by looking at a cusp. And what you find out when you look at Zellberg is that, okay, there are two things which don't match. There is first the fact that it's really two-dimensional, so you have a different growth. And the second thing that doesn't match is that when you look at the way the primes appear, they appear with the wrong sign. So here, what we have, if you want, we have a first hint of what really has to happen, and especially because of the fact that the Riemann zeta function has positive, imaginary and real zeros, then we find that it's extremely natural to have this kind of Minkowski type metric. Why black hole? Okay, this is really totally mysterious. I mean, it turns out that these black hole metrics are very natural and so on, but more than that, I mean, one can make them perfectly smooth by the technique of black holes. But and when you embed, moreover, when you make it periodic and you embed it in Minkowski space, it is a very beautiful picture. I mean, there is a compact piece which is coming from what happens on the interval, and then there are two infinite pieces which have a nice metric on them, which correspond to the non-trivial zeros. But okay, I mean, this has to be explored, and I mean, we don't know really.
But this operator W, I mean, the part towards infinity behaves in a way like cusp.
Yes.
Because, yes. I mean, this oscillatory behavior of the prolates, you know, of all the solutions towards the end points at infinity is exactly like, you know, would expect on a cusp, things on the cusp to behave. So it's a strange kind of one-dimensional operator which has some hidden two-dimension secret in it.
I mean, the most striking feature is the fact that, you know, normally when you take a one-dimensional manifold, of course, you have the number of eigenvalues which grows like linearly, like E. So even finding a case which is natural in which you have a growth like E log E was already quite a surprise, if you want, even though it's one-dimensional. I mean,
Okay, Jonathan, are you happy with the answers?
Yes, thank you.
Perfect.
Yeah.
Anybody else? Any further comments? Paul, you didn't ask any question.
Well, I mean, I think this is very fascinating to relate this very basic kind of analysis to Riemann Zeta. I think it's very fascinating, very interesting, and we shall see what happens.
the conclusion, yes.
Yeah, yeah. It's a right conclusion, yes.
Henry, just one more small question. So yes, any sort of your intuition or suggestions like how to continue to explore this geometric meaning of this? Like we have an operator, right? So we sort of study the spectrums in great detail, and then we know that they are sort of have a very close to the zeros of the Riemann Zeta function. So any sort of suggestions like how to build up this geometric meaning?
Well, the problem is not to build up, I don't know, the geometric meaning would help and maybe understand better. What is missing in this picture is a sort of more direct relation between the operator and the zeta. I mean, we just get, it's after the fact that we see that they are related, but it's a mystery. Why are they related?
Well, Riku, there I have to moderate what you say, because I mean, what happens is that really this operator, when you look at it, the Prolate operator, it's really the square of the scaling. Okay.
Yeah.
Yes. Plus a kind of lower order perturbation in terms of representation of SL2R, as we know. I mean, I will explain that. But so in a sense, I mean, it's not totally surprising that it's related to zero of zeta, because the scaling operator itself is related to the zeros, but it's related by an absorption spectrum, and here by the, I mean, you know, make it into an emission spectrum. So I mean, it's the mystery is not total, but as Riku says, of course, it's after the fact. But there is a relation. There is a strong relation.
Yeah, no, yes, along the way in which you set up the whole program, this is a relation, I mean, because the scaling plays a fundamental role in what you did. So of course, this is an improvement on the scaling.
Yeah.
That's clear.
Alan?
Yes, maybe one more question. How do you think, is there any hope that this spectral triple corresponding to this Prolate operator is some kind of limit in this Gromov-Hausdorff distance of maybe this spectral triples corresponding to this infrared part?
No, that's very difficult to say. No. You want to answer, Riku? Or?
No.
I mean, if it's a limit of the compactification of the two-dimensional Minkowski type geometry. I mean, that's the right type of limit you want to see. But then, if you want to input the primes, okay, that's another story. No. I mean, there could be, of course, okay. I mean, one-shot way, but without it. Okay.
Thank you.
All right, I think it's time to wind it up. I don't see any other volunteers to ask questions or make comments. So let us thank Riku again for a very fascinating talk.
Thank you for listening.
Our pleasure. And this way, I am announcing formally the end of the academic year 21, 22. So you acted, Henri, as a terminator. You terminated the semester. And I hope to see you guys back in October. I don't know exactly the dates yet, but when I get the slides uploaded, I'll send an email with links to a video and so on. So for the time being, thank you so much for seeing you, for being here, and I very much hope to see you next academic year. Okay, all the best.
Thank you.
Bye-bye.
Thank you. Bye-bye.
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 Henry.
Bye-bye.
Yes.